Good morning everyone. I am Dipanshi from BSc Chemistry Unit second year. Today I am here to discuss the topic colloids. What are colloids? A colloid is a substance microscopically dispersed to the another substance. The word colloid comes from a Greek word kola which means glue. Thus colloidal particles are glue-like substance. These particles pass through a filter path but not through a semi-permeable membrane. Colloids can be made settled by the process of centrifugation. A dispersed phase in which a discontinuous phase and a dispersion medium a continuous phase. The dispersed phase particles have a diameter of between approximately 1 nanometer to 100 nanometer. Such particles are normally invisible in an optical through their presence can be confirmed with the use of an ultra microscope or electron microscope. Now what are solutions? Solutions are made up of particles or solutes of and a solvent. The solvent part of solution is usually a liquid but it can be a gas. The particles are atoms, ions or molecules that are very small in diameter. Colloidal mixture has particles that are not as small as the solution and as not as large as suspension. The particles are intermediate in zinc. Suspensions made up of particles and a solvent. Its particles are larger than those found in a solution. The particle in a suspension can be distributed throughout the suspension evenly by shaking the mixture. Now, solution table salt dissolved in a water to form salt water. A solute NaCl is dissolved in another substance water known as solvent and this creates a solution. Floor suspended in water appears light blue because blue light is scattered off the floor particles to a greater extent than red light. Milk is an emulsified colloid of liquid butterfat globules dispersed within a water-based liquid. Colloids are stabilized by suspension by electrostatics mutual repulsion of like electrical charges. Now comparison of the properties solution colloids and suspension. Property particle size. In true solution less than 1 nanometer, colloid 1 to 100 nanometer and more than 100 nanometer in suspension. Appearance clear, cloudy and in suspension also cloudy. Homogeneity homogeneous or heterogeneous. Transparency transparent but often colored, often translucent and opaque but can be transparent, often opaque but can be translucent. Separation does not separate, can be separated or settles. Filtrability passes through filter paper. Particles do not pass through the filter paper. Example of colloids are milk, synthetic polymers, fog, blood, jam, shoe polish, smoke, etc. The following forces play an important role in the attraction of colloid particles. Excluded volume repulsion and the liquid theory. In the liquid theory state that the excluded volume of a molecule is the volume that is inaccessible to the other molecules in the system as a result of the presence of the first molecule. The excluded volume of a hard sphere is 8 times its repulsive forces between molecules other than those due to covalent bonds, the hydrogen bonds or the electrostatic interaction of the ions with another. Electrostatic interactions. The colloidal particles often carry an electrical charge, therefore attract or repel each other. The charges of both the continuous and the dispersed phase as well as the mobility of the phases are factors affecting. Steric forces. Steric forces arise from the fact that each atom within a molecule occupies a certain amount of space. If the atoms are brought too close together, there is an associated cause in the energy due to the overlapping of electron clouds. Poly or bond repulsion, and this may affect the molecule's preferred shape and reactivity. Classification of colloids. Based on physical state, dispersed phase and dispersion medium. Based on nature of interaction between dispersed phase and dispersion medium. Based on molecular size in the dispersed phase. Based on the appearance of colloids. Based on the electric charges on dispersion phase. Based on physical state, dispersed phase. Here is dispersed medium. Name and example. Solid in solid, solid sol, and examples are alloys, glass, solid and liquid sol, ink, blood, solid and gas aerosol, smoke, ice, cloud, and liquid and solid gel, jelly, curd, liquid and liquid emulsion, milk, cream, liquid in gas, liquid aerosol, cloud, fog, gas in solid, solid form, aerogel, pumice stone, gas in liquid form, shaving cream, gas in gas, none, all gases are miscible. Based on the nature of interaction between dispersed phase and dispersion medium. Lyophilic colloids. Colloidal solution in which the dispersion phase has a great affinity for the dispersion medium. They are also termed as intrinsic colloids. Such substances have tendency to pass into colloidal solution when brought in contact with dispersion medium. If the dispersion medium is water, they are called hydrophilic or emulsioids. The lyophilic colloids are generally self-stabilized, reversible in nature, and are heavily hydrated. Example of lyophilic colloids are starch, gelatin, rubber, protein, etc. Lyophobic colloids. Colloidal solutions in which the dispersed phase has no affinity to the dispersion medium. These are also referred as extrinsic colloids. Such substances have no tendency to pass into colloidal solution when brought in contact with dispersion medium. The lyophobic colloids are relatively unstable. They are irreversible by nature and stabilized by adding small amount of electrolyte. They are poorly hydrated. If the dispersion medium in water is lyophobic colloid, are called lyophobic or suspenoids. Examples: salts of metals like gold, silver, salts of metal hydroxide, and salts of metal sulfides. Based on molecular size and dispersed phase. Multimolecular colloids. Indivisible particles of the dispersed phase consist of aggregates of atoms or small molecules having diameter less than 10 raised to the power 7 cm. The particles are held by weak van der Waals forces. Macromolecular colloids. The particles of dispersed phase are sufficiently large in size enough to be of colloidal solution. These are called natural polymers. Associated colloids. These colloids behave as a normal electrolytes at low concentration but behave as colloids at higher concentration. These associated colloids are also referred as micelles. Sodium stearate C18H35NaO to behave as electrolyte in dilute solution but colloid in higher concentration. Example: soap, higher alkyl sulfonates, polyethylene oxide. How does soap work? When greasy desert dirt is mixed with the soapy water, the soap molecules arrange themselves into tiny clusters known as micelles. The water-loving hydrophilic part of the soap molecules stick to the water and point outwards, forming the outer surface of micelle. The oil-loving hydrophobic parts stick to the oil and trap oil in the center where it cannot come into the contact with the water, with the oil tucked safely in the center. Based on the appearance of the colloids. Sols. When a colloidal solution appears as a fluid, the sols are generally named as dispersion medium. When the dispersion medium is water, the sol is known as hydrosol or aquasol. When the dispersion medium is alcohol or benzene, it is called alkosol or benzosol. Gels. When a colloidal solution appears as solid, the rigidity of gel varies from substance to substance. Example: jelly, butter, cheese, and curd. Based on the electrical charge on the dispersion phase. Positive colloids. When dispersed phase is in a colloidal solution carries a positive charge. Example: metal hydroxide like FeOH3, AlOH3, methylene blue sol, etc. Negative colloids. When dispersed phase in a colloidal solution carries a negative charge. Example: silver sol, copper sol. Separation of colloids. Mechanical dispersion, electrical dispersion, or Bragg arc peptidization condensation method. Mechanical dispersion. In this method, the substance is first ground to coarse particles. It is then mixed with the dispersion medium to get a suspension. The suspension is then grinded to an colloidal mill. It consists of two metallic discs nearly touching each other and rotating in opposite direction at a very high speed, about 7,000 revolutions per minute. The space between the disc of the mill is so adjusted that coarse suspension is subjected to the great shearing force, giving rise to particles of colloidal size. Colloidal solution of black ink, paints, varnishes, dyes are obtained by this method. Now second method B, by electrical dispersion or Bragg's arc method. This method is used to prepare sols of platinum, silver, copper, or gold. The metal whose sol is to be prepared is made at two electrodes which emerge in dispersion medium such as water. The dispersion medium is kept cooled by ice. An electric arc is struck between the electrodes. The tremendous heat generated by this method gives colloidal solution. The colloidal solution prepared by stabilized by the adding a small amount of QH to it. By peptidization, the process of converting a freshly prepared precipitate into colloidal form by the addition of suitable electrolyte is known as peptidization. Cause of peptidization is the absorption of the loss of the ions by the electrolyte by the particles of precipitate. The electrolyte used for this purpose is called peptidizing agent or stabilizing agent. Important peptidizing agents are sugar, gum, gelatin, and electrolyte. Condensation method. In the condensation method, the smaller particles of the dispersed phase are aggregated to form larger particles of colloidal dimension. Some important condensation methods are solution of substances like mercury and sulfur are prepared by passing their vapor through cold water containing a suitable stabilizer such as ammonium salt or citrate. By excessive cooling, a colloidal solution of ice as an organic solvent either by chloroform can be prepared by freezing a solution of water into solvent. The molecules of water which can no longer be held in the solution separately combine to form particles of colloidal seed by exchange of solvent. Colloidal solution of certain substances such as sulfur, phosphorus which are soluble in alcohol and insoluble in water can be prepared by pouring their alcoholic solution in excess of water. For example, alcoholic solution of sulfur on pouring into water give milky colloidal solution of sulfur. Chemical methods. Colloids can be prepared by following chemical methods. Oxidation. Addition of oxygen and removal of hydrogen is known as oxidation. For example, colloidal solution of sulfur can be prepared by oxidizing an aqueous solution of H2S with an suitable oxidizing agent such as bromine water. H2S plus Br2 gives 2HBr plus sulfur. 2H2S plus SO2 plus gives 2H2O plus 3 sulfur. Addition of hydrogen and removal of oxygen is called reduction. For example, gold salt can be obtained by reducing a dilute aqueous solution of gold with stannous chloride. Hydrolysis. It is a breakdown of water. Salts of ferric hydroxide and aluminum hydroxide can be prepared by boiling the aqueous solution of the corresponding chloride. For example, FeCl3 plus 3H2S gives FeOH3 plus 3HCl. Double decomposition. The salts of inorganic insoluble salts such as arsenous sulfide, silver halide, etc. may be prepared by using double decomposition reaction. For example, arsenous sulfide of salt can be prepared by H2S gas through a dilute aqueous solution of arsenous oxide. As2O3 plus 3H2S gives As2,3OH3 plus 3H2O. Donham membrane equilibrium. When two solutions containing electrolytes are separated by a membrane which is impermeable to one of the ions of the electrolytes, it was found that at equilibrium an unequal distribution occurs for the permeable ion on both the sides of the membrane. At equilibrium, the osmotic pressure of two solutions will be different if the two reference electrodes such as calomel electrodes and put it into the solution, then a difference of potential will be set up. This type of equilibrium is known as Donham. Components of a solution. Internal solution. It is a solution of an electrolyte containing non-penetrating ions of about colloidal dimension and ions small enough to be penetrate. External solution. It is a solution of electrolyte containing both penetrate ions. Semi-permeable membrane. It separates the two solutions impermeable to all. Purification of colloid. There are three common methods: dialysis, electrodialysis, ultrafiltration. Dialysis. The process of separating particles of colloid from those of crystalloid by the means of diffusion through a suitable membrane. Its principle is that colloidal particles cannot pass through a cellophane membrane while the ions of the electrolyte can pass through it. The impurities slowly diffuse out of the bag, leaving behind pure colloidal solution. The distilled water is changed frequently to avoid accumulation of the crystalloids, otherwise they may start diffusing back into the bag. Dialysis can be used for removing HCl from the ferric hydroxide solution. Electrodialysis. The process of dialysis is very slow. The process is speeded up by the application of electrical potential. This is called electrodialysis. You can see also. Now the application of electrodialysis. Artificial kidney machine can make use of electrodialysis. Ultrafiltration is a process of high pressure filtration through a semi-permeable membrane in which colloidal particles retain while small size solutes and solvent are forced to move across the membrane by hydrostatic pressure. Application of ultrafiltration. Ultrafiltration is a vital process that takes place in the kidneys. Properties of colloids. Physical properties. Heterogeneity. Colloidal solution consists of two-phase, dispersed phase and dispersed medium. Visibility of dispersed particles. Dispersed particles present in them are not visible to the naked eye and they appear homogeneous. Filterability. The quality of particles pass through an ordinary filter paper, however, they can be retained by animal membrane, parchment, cellophane membrane, and ultrafilter. Stability. Lyophilic salts in general, lyophilic salts in the absence of substantial concentration of electrolytes are quite stable. Color. The color of a colloidal solution depends upon the size of colloidal particles, and large particles absorb the light of longer wavelength and therefore transmit light of shorter wavelength. Optical properties of colloid. Tyndall effect. When an intense coveraging of beam of light is passed through a colloidal solution kept in dark, the path of beam gets illuminated with a bluish light. This phenomenon is known as Tyndall effect, and the illuminated path is known as Tyndall quad. The Tyndall effect is due to the scattering of light by the colloidal particle. Tyndall effect is not exhibited by true solution. This is because the particles present in a true solution was also small to scatter. The Tyndall effect can be used to distinguish a colloid solution from a true solution. The phenomenon has also been used to devise an instrument known as ultramicroscope. This instrument is used to increase for the detection of particles from colloidal dimension. Mechanical properties. Brownian movement. The continuous zigzag movement of the colloidal particles in the dispersion medium in a colloidal solution is called Brownian movement. Brownian movement is due to the unequal bombardment of the moving particle molecules with dispersion medium on colloidal particles. The Brownian movement decreases with an increase in the size of colloidal particles. This is why the suspension do not exhibit this type of movement. Thank you.